Okay. So I'm Chinwendu Enyioha. I'm in the ECE department at UCF, and thank you guys for this opportunity to share a little bit of my work and interest. I joined UCF a couple of years ago, and I direct the Autonomous and Intelligent Systems Lab and the newly formed Unmanned Aerial Systems Lab that's joined with the L3 Harris company. I have a background in math, and I'm generally interested in dynamical systems, controls, especially resource-aware techniques in control decision making, distributed optimization, with applications to a broad range of systems. The examples I'm going to talk about today are cyber-physical systems and the constraints they present. I've so far taught control courses at UCF with interest in expanding that to network control and courses in optimization. I have two PhD students and two undergrads and one master student. That's my group. Um, I'm motivated by systems we see around us every day, the power grid with which we interact, the emerging commercial Internet of Things type systems. These systems, these two as an examples, are obviously large. There's always the need to balance things happening on different ends. For example, in power networks, balancing supply and demand, figuring out how to get information to where we need them for decision making. In the IoT systems, for example, and it turns out that even though the approach we take on these problems are, theoretical in some sense, the applications are real, right? We can't have or tolerate delays in certain systems. In some examples, we don't even know much about the environments in which we operate. So the need and the size of these systems generally means that we can we need to find ways of distributing or decentralizing computations and decision making in a way that results in the global behavior we want. And the overarching goals are how efficient can we be in designing algorithms for the system, how fast can those be, and how well do they scale, right? So scalability is a big issue, a big challenge in this space. I'm going to present three, projects in this general space, highlighting some challenges and some efforts along those directions. So again, these systems present us with so many challenges, and the question is how do we attack them from a computation viewpoint and optimization angle? The first is one in distributed optimization. You have a large system and you want to have the agents collectively accomplish a goal. Typically, we think of these goals as represented by functions that capture the tasks. The functions sometimes may be well structured or not too well structured. So the goal here is how fast can we solve this when each agent is like making decisions on their own. If the goal is accomplished when the function is at its minimum, then that's the objective of the system. There are different approaches to addressing these kinds of challenges, but it matters how fast things are done. In a distributed system, you want agents locally deciding and interacting with each other as they solve this problem. Like I said, the method we choose matters a lot because, as you can see, one method, the one to the left, there solves the problem fairly fast or significantly faster, at least an order of magnitude faster than other related methods, like the BFGS I'm going to present. The approach for this problem was to use an adapted Parzival-Bowen method that, as you can see, solves this problem in a distributed way for a symmetrical undirected network, right? These methods on this slides are not very common these days because I think for those who are kind of familiar with the area, the general approach is to use, even in machine learning, gradient-based methods or gradient methods. But those methods are known to be very slow, as you can see on the image to the right. So the question is, what could we do? And not just, solve this and show that it works, but the main interest, at least for my group, is deriving guarantees, like actually showing or deriving results for these sorts of systems. So we've shown in this project that for a network objective that's not too well structured, we can actually solve and solve the problem with an algorithm that's converges at a linear rate, which is good for not so well structured problem. And as we can see, the methods we're using here outperform more commonly used methods, right? The second project I want to highlight is one on limited communication. You have a power network, information flows on the red dots there, as you can see, and power flows using the black dots or the black lines. The goal of the operator there is to balance supply and demand. And the question is, how can that be done with two particular constraints? Because of how the system operates, users don't let the operator know how much power they want to consume. I'm sure in our homes, we just plug in our devices and use power. But the coordinator needs to find a way to incentivize us not to violate the capacity constraints, because blackouts can result. And the computation question in that is, how does the information flow affect satisfaction of these constraints and solution to the problem, right? We took an approach using a somewhat well-structured task here to relate information compression, how many bits of communication is needed, and how well the constraints they are satisfied. So essentially bringing together system like transient constraints in the system, information compression or quantization, and how many bits of information we use. As we can see, if you have a compression scheme, in the second diagram to the right there, if you have a compression scheme that is not taking into account constraints of the system, yes, you violate those constraints, and that's a problem. On the other hand, when you take a compression scheme, the PF scheme, that takes into account the constraints of the system, yes, you can see that obviously there's a trade-off between how soon you attain the objectives and and how the compression scheme affects that. So it's possible for problems that are not so well structured, or objectives that don't give you the best forms, to still solve them without necessarily using full information in coordinating the operation of such a system. And we can also clearly, when I say clearly, I mean analytically, show the relationships between parameters at play. What algorithms does one use? How accurate can you be? And how much information do you need to transmit in solving that problem? And this is something that we use every day, right? Power consumption, and trying to be sure that we don't exceed the capacity of the system. The third problem is a little bit related to what we're going through these days. So I'm sure many of us have seen this image and how the goal of Washington, D.C., or Tallahassee in our case, is to reduce R0 so we can get back to work and all of that. For this particular virus, or certain viruses in general, the population cannot be assumed to have been well mixed, right? Which means that we need to take into account the actual interaction structure. But it turns out for a problem like this, where yes, we do want to reduce R0, the structure of the network alone can't get us there. And the question is, how do we take into account certain algebraic properties of the network that affect this reproduction number? A while ago, we looked at this problem of allocating just two resources, vaccines, medications. Today, obviously, with these several approaches we've seen, you can scale this up to more intervention approaches. How do we reduce the cost of controlling the outbreak and be sure that we actually control it, that R0 is reduced? This problem was considered on a directed network. The network was formed from looking at flights within the US, 74 airports with high traffic, just figuring out how to allocate vaccines for sub-airports, or if you may, medications. We can see that in the image to the left, where you take into account just the structure, yes, it has a similar form to taking more than the structure into account. However, there are nuances. And for a directed network like this, or a directed graph, it's not an easy problem. We can also be interested, as we showed, in looking at what happens to controllability properties of a network as the size increases. At what point, or for what classes of networks, do you lose the ability to control them? We showed and derived like justifications, bounds that on the network classes that can be controlled even as the sizes increase, and why that's the case using the controllability Gramian. I'm interested in looking at the information structure, the relationship between information structure and computation using different, commonly used algorithms, taking into account constraints that certain systems we look at present us, and finding out how those affect computation on those systems, and especially with respect to control or decision making in unknown, dynamic, a little bit of uncertain environments. That's a continuation of the little bit of what I presented today. And then the newly formed lab with L3 Harris is looking at somewhat related problems, DoD style problems, if you may. So typical command control, how to accomplish certain missions in, tough terrains and all of that. Can't say much more than L3 Harris has on their website about that. And I'm also interested in looking at security of cyber physical systems, particularly how the difference in time scales of operation of these systems affects safety, as an important property. As an example, a vehicle, the physical dynamics of a vehicle happen at a somewhat slow pace than computations that guide that operation. The interaction between these two are things of interest. I'm also interested in the broad area of reinforcement learning, where you have multiple agents that are potentially competitive, trying to figure out the environment and make decisions in that environment. And I have this cartoon there to show that these are not just like engineering systems, so they could be systems involving humans, which means if folks have interesting applications where these keywords could show up, there's an interest in relating, interacting, and collaborating. That's what I have. Hopefully I'm good at time.
Okay,